Welcome back. So hopefully you had a good time about the last lecture talking about the physical meaning of the determinant. Well, for some students, they have learned the determinant in our classes before. However, they have trouble understanding the meaning of that. So that's why we chose the geometry definition to show you how the definition of determinant formed and how we're going to use it. And that's the core content of today. Alright, so let's look at how we're going to use the knowledge or the geometry definition of determinant. So for example, in the 2x2 determinant condition, we have something like this, right? Have this one row vector here and this row vector here. And we can have them to form a parallelogram. And we can calculate the area. And apparently, the area does not equals to 0. So this means these two vectors, this one and this one, are not linear dependent, or to say they're linear independent. So we can say that, yeah, because for this vector, it can never be expressed by this vector. So that's why they can make a parallelogram with a certain area, and that's why we call it linear independent. However, for example, if we rotate the two vectors, for example, we rotate this one to a little bit unclockwise, so form something like this. Now we can see that apparently, well, the new parallelogram we have a smaller area, and if in a very extreme condition we further rotate this, unclockwise, we're gonna end up something like this. It means, well, these two vectors will be overlapped. So let's look at one example. So if we have a 2x2 determinant, which is given by 1, 2, and 2, 4, right? And this is the row vector 1, 2. And this is the row vector 2, 4. And we can see that they're all in the same straight line. So we understand they actually cannot make a valid parallelogram, or to say that they can make one. But the one is with the area as 0. So we can, say that, the determinant's value for this 2x2 determinant is 0. So when the determinant is 0, we can say, in a contrast with this condition, we will say these two vectors are linear dependent. And just because we can see that those two vectors are actually aligned within the same straight line. Well, that's from the point of view of the geometry. If you do some algebra test, you can see that for the first row vector 1, 2. Now we have this simplified form still as 1, 2. If you do 2, 4, we will have the simplified form for this ratio as 1, 2. So actually they are the same, right? So that's why they are aligned within the same straight line. And so that's why we call it linear dependent, because actually the first row vector 1, 2 can be used to express the second vector 2, 4. As we can see that, well, although the 2, 4, this one is longer, however, we can just use, for example, 2 times 1, 2. Yeah, to express, well, such vector 2, 4. So that's why, we would call it linear dependent. Okay, so we actually can expand this to the 3x3 determinant, which will give us the volume here. Yeah. So for example, so if this one, So we have, this vector here, v1, v2, and v3, right? So for example, if the v3 somehow get into the plane composed by v1 and v2, I will enlarge it here. Okay, so this is v1 and this is v2. Apparently, they're not linear dependent, or to say they're linear independent. So that's why they can form a plane here with a certain area. However, the v3 are rotated, all the way up to be within such plane composed made by v1 and v2. Somehow, for example, v3 is here. Yeah, so it means v3 can be, expressed by v1 and v2, right? By certain, with a certain coefficients here. So that's why we call it, yes. If v3, this vector is within the plane made by v1 and v2, there's no volume. And we will say the volume will be 0. So similarly, we will call it v1, v2, and v3 are linear dependent. Okay, so we can also expand this linear independent and dependent situations all the way to the n-dimensional. Alright, so for today's homework, you can try to think about the n-dimensional linear independent or dependent situations based on the top, the n-dimensional volume. Alright, you can think about this. And, the linear dependent and independent properties are very, very important. I would say that I will give something like this. Very important. We can use it a lot later. And also, this is one of the most significant knowledge within the linear space, which is core of linear algebra, and that's why we call it linear algebra. So think about this, and I will see you in the next lecture.